What's up, Mustangs? Miss Titus here, and today what we're going to discuss are linear versus nonlinear functions. So we've been talking a lot about equations of lines and the equation y equals mx plus b, and this is a linear equation. We know it's linear for a couple of reasons. Because it has a plane x, because the graph is a straight line, and because it has a constant rate of change. So that's what I'm going to highlight here. The way that we can tell something is linear, so I'm going to write it down here. Linear equals constant rate of change. And remember that rate of change is just another name for slope. We already know this. So let's look at some examples. We're going to look at how to identify linear and nonlinear equations. Graphs. And tables. Okay, so we're going to look at equations, graphs, and tables and identify linear versus nonlinear functions. Now, think back to when we talked about parent functions. We talked about a couple of different parent functions. I'm going to flip to that page real quick in my iPod. We talked about linear parent functions, quadratic parent function, and exponential parent functions. So when I say linear and nonlinear, I mean linear being in this family. Nonlinear would be any other family. So it's a big group for a couple of ideas. Quadratic, exponential, cubic, lots of different things. So let's get started. If we open up our equations tab, I can see here, I'm going to list some examples and non-examples. But first let's define. If we're looking at an equation, how can we tell that a function is linear? Okay? So remember that the most common form of a linear function is y equals mx plus b. So the first thing is that x has no exponent and we have a slope, which is a constant rate of change. So what does that look like? Well, some examples might be y equals 3x plus 2. We have x raised to the first power, and we have a slope of 3. 1/2 x minus 5. We have an x raised to the first power and a slope of 1/2. We can have 3x plus y equals 6. Again, x is raised to the first power. And 2x plus 5 equals y. Again, it doesn't matter where x is. It doesn't have to be perfect y equals mx plus b form. It just has to have an x raised to the first power with a slope or a coefficient. Okay, so some non-examples. Well, anything quadratic, right? So we could say y equals 3x squared plus x. This is going to be a quadratic function. X here is raised to the second power, and there's no constant rate of change. Whenever y or x is in the denominator, this is also not considered linear. Or what we talked about before, exponential functions. Y equals 3 to the power of x. If x is in the exponent, this is also nonlinear. So if we look at examples, we can see examples of linear equations and nonlinear equations. Next, let's talk about graphs. We already know from our linear parent function discussion that linear functions create graphs that are straight lines. And the reason that the line is straight is, again, because we have a constant rate of change. Okay, so we talked about a couple of examples. We said straight lines can have positive slopes, they can have negative slopes, or they can have zero slopes. They can be horizontal lines. Okay, so we have positive slopes, negative slopes, zero slopes. All of these lines are considered linear. Now some non-examples. Think back to quadratic equations. We said quadratic equations are parabolas. They make a U shape. So this is not linear. This function right here, which is in trig, which you haven't even learned yet, is not linear because it has curves. It's not a straight line. And also, any vertical line is not going to be linear because it's not a function. Okay. So moving on, the last way and probably the most difficult way to identify linear versus nonlinear functions is by looking at a table. Okay, so if you see a pattern here, each of these is defined by a constant rate of change. What that means in a table is that x and y change by constant amounts. Which is our delta y over delta x. It has to be a constant slope. Now, here's a helpful hint. Make sure you always simplify your fraction because the fractions might be the same unsimplified, but once you simplify them, you'll see the same slope. So let's look at an example and a non-example. So we'll draw a little table here. I have 1, 2, 3, 4, and 2, 4, 6, 8. If I look over here, my delta y is always going to be 2. My delta x is always going to be 1. So I can say that my constant rate of change is 2 over 1, which is equal to 2. Okay? Now, sometimes our rate of change will not always be the same numbers, but when we simplify them, they'll be the same. So let's look at an example right here. Okay, so I have x and y. I'm going to have negative 2, 10. I'm going to have 0, 9. And then I'm going to have 4, 7. Okay. From 10 to 9 is minus 1. From 9 to 7 is negative 2. Negative 2 to 0 is plus 2. And 0 to 4 is plus 4. So my ratios end up being negative 1/2 and negative 2 over 4. But when I simplify negative 2 over 4, it's actually equal to negative 1/2. So even though my rates are different, they end up simplifying to be the same thing. So let's look at a couple of non-examples. These tables are not going to have constant rates of change. So if I have 1, 2, 3, and then I have negative 10, 10, and 0. Well, from negative 10 to 10, that's going to be plus 20. And from 10 to 0, that's going to be minus 10. Over here, I have a constant change of 1. So that's going to give me two different rates, 20 over 1 and negative 10 over 1. Because I don't have a constant rate of change, this table is not linear. Alright guys, that's all I have for linear versus nonlinear. Now what you're going to do is you're going to have a card sort. I'm going to give you a set of cards and you're going to separate them into groups of linear functions and nonlinear functions. That's it, and as always, staying strong.